All right, get this. Picture a galaxy. Bright, like blazingly bright, like our own Milky Way, but crammed into a space like 100 times smaller. Yeah, you heard that right. That's what the James Webb Telescope, JWST, just spotted. And let me tell you, it's sending shockwaves through the astronomy world. We're talking early galaxies, the kind from the universe's baby book, growing way faster than anyone thought possible. So today, we're going deep dive style into this mystery of how these galaxies bulked up so fast, ready to explore.
Yeah, it's like the universe hit the fast forward button on galaxy formation. We were expecting, I don't know, faint little signals, right? Like little baby galaxies. It's just starting to clump together. But no, we're seeing these massive, bright galaxies already hogging the cosmic spotlight. And it's happening way earlier than we thought possible.
It's kind of mind-blowing, right? Like, think about it. Our current best theory, the one with cold, dark matter, the invisible stuff that's supposed to be like the scaffolding for galaxies, well, it works pretty well for the galaxies we see closer to home, but it just can't keep up with the speed at which these early giants formed.
Right. Cold dark matter likes to take its time. It's all about slow, gradual growth, galaxies merging together over billions of years. But these JWST observations, they're like, nah, we don't have time for that. We're going big and we're going fast.
It's almost like finding a skyscraper where you expected a log cabin. Just boom, instant galactic city. And this is where things get really interesting, right? Because there's this other theory. It's been kind of waiting in the wings, for its chance to shine.
Hmm.
And it's called MOND, Modified Newtonian Dynamics. And it might just explain what cold dark matter can't.
Yeah, MOND. It's been around for a while, kind of like that friend who always has the crazy ideas. But sometimes those crazy ideas turn out to be brilliant.
Exactly.
The
So what is MOND and why is everyone suddenly talking about it?
Well, the basic idea is that gravity at those mind-bogglingly huge distances we're talking about, at the edges of galaxies with incredibly weak forces, it might not work exactly as Newton described it. See, with MOND, instead of needing dark matter to explain why galaxies spin faster than they should, it suggests maybe, just maybe, we need to tweak how gravity works at those scales, like a little adjustment to the cosmic rulebook.
So instead of adding new stuff to the universe, MOND says, hey, let's just fine-tune the laws a bit. And here's the thing that really makes you go, MOND predicted these big, bright galaxies, like way back when, decades ago.
Exactly. And there's this astrophysicist, Stacy McGaugh. He's at Case Western Reserve University, and he's been studying MONE for years. Well,
Huh.
in his recent research, published November 12th, he pretty much said, and I'm paraphrasing here, I told you so. And honestly, you don't often see a theory's predictions get confirmed so dramatically.
Talk about a mic drop moment. But hold on. I've heard some scientists are saying that some of these super bright objects JWST is seeing might not be full-blown galaxies, but actually supermassive black holes.
Yeah, that's true. Some are saying that. But here's the thing. Even if some of them turn out to be black holes, it just, it kind of shifts the problem, right? Instead of too many early galaxies, we'd have too many early supermassive black holes, which is, well, equally weird. It's like, no matter what, something unexpected is going on in the early universe, and we need an explanation. It's like a good detective story, you know? You gotta follow the clues. So let's dig a little deeper into this MOND thing. It's not just some random idea. It came about trying to explain this other puzzle that's been bugging astronomers forever. It has to do with how galaxies rotate.
Oh, yeah. Yeah, I remember hearing about this. Something about galaxies spinning, like way faster than they should, based on the stuff we can actually see, the stars and gas and all that.
Exactly, exactly. For decades, astronomers, they've been pulling their hair out over this. You see, according to like Newton's law of gravity, stars way out on the edge of a galaxy, they should be moving like way slower than the stars closer to the center. Just like, planets further from the sun, they orbit slower.
Right, right. Makes sense, I guess. Further away from the gravity source, the weaker the pull should be.
Right, yeah. But here's the thing. Observations show that stars on the outskirts of galaxies, they're zipping around way faster than they should if we only consider like the stuff we can see, the visible matter, the stars, gas, dust, all that. So it's like something's missing. Something's adding this extra gravity, to keep those outer stars from just flying off into space.
And that's where dark matter comes in, like
Yeah.
the cosmic glue, the invisible stuff holding everything together.
Yeah, precisely. Dark matter, it was like proposed to explain that missing gravity. It's this mysterious stuff, can't see it, doesn't interact with light, hence the name dark, and it's thought to be like a huge chunk of the universe's mass, providing that extra gravitational oomph to explain those those super fast galactic rotations.
But then MOND comes along and says, hold on a second. What if we don't need to, like, invent this invisible stuff?
Oh,
What if it's just, like, our understanding of gravity that's a bit off?
exactly, yeah. MLD's like, what if at those crazy weak gravity levels way out there on the edge of galaxies, what if gravity, like, acts a little differently than we thought?
So instead of adding new ingredients to the cosmic recipe, Emily's like, let's just adjust the cooking instructions a bit.
Ah, I like that. And remember, this isn't just like pulling stuff out of thin air. MOD's been making pretty accurate predictions for decades. And now these JWST observations, well, they seem to back it up even more.
But if Mamondi is so good at explaining things, why hasn't it just, like, taken over, totally replaced the whole dark matter idea?
Well, there are a few reasons. First, even though MOD does a really good job of explaining like how individual galaxies rotate, it's had some trouble explaining some other stuff on a bigger scale, like the distribution of galaxy clusters and how light bends around really massive
So
objects.
it's like MOD fixed one problem but maybe created another one somewhere else.
Yeah, kind of like that. And then, dark matter, it has its own issues too. Even though we've been looking and looking, we still haven't directly detected any dark matter particles. And while it fits a lot of observations, it doesn't perfectly explain everything. There are still some puzzles out there.
So both theories have, like, their wins and their losses.
Exactly, exactly. And now with the James Webb Telescope, it's like it's adding this whole other layer of complexity to the puzzle. Like the
Uh,
universe is saying, "Think you've got me figured out. Think again."
She's like watching a tennis match, like a really intense one between two, like, Grand Slam champions. Each player's got their strengths, their weaknesses, and every point, it matters.
Yeah, and the audience, in this case, scientists and everyone who's fascinated by space, well, we're all on the edge of our seats, waiting to see who wins in the end. Or maybe, just maybe, there's a totally different ending, something we haven't even thought of yet.
It really makes you realize, yeah, how much we still don't know about the universe.
Yeah.
It's, like, humbling and exciting at the same time.
It really is. And it's like a constant reminder that science it's a journey. It's not about like reaching the final destination.
Yeah.
And these unexpected discoveries, that's what keeps us going. That's what keeps us curious.
So where do we go from here? Like, what's the next move in this cosmic game?
Well, the James Webb Telescope, it's going to be like front and center. Astronomers are going to be using it to study these early galaxies in even more detail. They'll be looking for any tiny clue that can help us like tell the difference between cold dark matter and MOND, or maybe even point to like a totally new theory.
It's like we've been given this amazing new tool,
Yeah.
and we're just starting to figure out all the incredible things it can do.
Yeah, exactly. We're just scratching the surface of what the James Webb Telescope can show us about the early universe, and even beyond this whole dark matter versus MOND thing. These observations are making us rethink some pretty basic ideas about how galaxies form and how they evolve.
It's like a chance to rewrite the textbooks,
Yeah.
to redraw the maps of the universe, and who knows, maybe even change how we see our place in it all.
And what's really fascinating is that, these questions, they go beyond just astronomy. It's like they touch on the very essence of how we do science. Like how do we build these models of the universe? How do we test them? And what happens when they don't quite fit?
It's a good reminder that science is always changing, right?
Yeah.
We're always challenging what we think we know. We have to be open to new ideas, even the ones that seem, I don't know, kind of crazy at first.
Exactly, yeah. And it's that willingness to embrace the unknown, to question what we think we know. That's what lets us push the boundaries of what we understand.
So let's bring this back to our listeners, the folks who've been with us on this deep dive. What is all this? What does it all mean for them? For anyone who looks up at the night sky and just wonders about it all.
It means that, every time you look at those stars, those galaxies, you're looking at a mystery waiting to be solved.
Yeah.
It means that what we know about the universe, it's always changing, it's always evolving. And that's pretty amazing, you
Yeah.
know?
Yeah, it reminds us that we're part of something so much bigger than ourselves, something that's still full of surprises, and that feeling of awe, that drive to explore and understand. That's what makes us human. So to wrap things up, I guess what we've learned is the James Webb Telescope, It's showing us a universe that's even more amazing, more complex than we could have imagined. And these early galaxies, these giant bright galaxies that we're finding, well, they're shaking things up. They're making us rethink the whole dark matter thing, and they're giving MOND, that underdog theory, a real chance to shine.
And while we don't have all the answers yet, this journey of discovery, it's just getting started. The James Webb Telescope, it's going to keep giving us clues, keep giving us those tantalizing hints, and who knows, who knows what other secrets it'll uncover.
It's it's a pretty amazing time to be, looking up at the stars, wouldn't you say?
Absolutely. Absolutely. And who knows, Who knows what else is out there waiting for us. Until next time, keep looking up.
All right, let's dive into this supermoon spectacular. The final one of 2024. Can you believe it?
Time flies when you're gazing at the stars.
It really does, especially when those stars include a supermoon.
Oh, yeah, this one's going to be special.
Definitely bigger, brighter, and way more awe-inspiring than your average full moon.
You ready for the full Beaver Moon?
Oh, absolutely. Friday, November 15th. Mark it on your calendars, folks.
Actually, what's really cool? The moon will look full for a couple nights, even before and after that exact moment of fullness.
So it's not just a Friday night thing. We can enjoy it all weekend.
Yeah, exactly. It's kind of like, have you ever hiked up a mountain?
Oh, tons of time.
You know how you're surrounded by the awesomeness of the mountain, even when you're not at the very, very peak?
You're already in the zone.
Right, exactly. You get that build up and then you're still kind of basking in it afterward.
I love that analogy. So we've got this whole supermoon weekend to soak it all in. And to make things even better, there's something else going on up there. Hanging out right next to our lunar superstar, the Pleiades star cluster in Taurus.
Oh, nice.
The Seven Sisters. Ever heard of them?
Oh, of course. Who hasn't? They've been fascinating people for centuries. Like in Greek mythology, they were the daughters of Atlas turned into stars to escape Orion.
I love that story.
And in indigenous Australian cultures, they were seen as seven sisters running away from an ancestor.
It's amazing how these same stars have so many different stories woven around them.
It is, right. All these different cultures looking up at the same sky and coming up with these incredible stories.
Absolutely. But with the full moon shining so brightly, do you think it'll be tough to spot all seven sisters?
Yeah, probably. It might be a little tricky. When you have something as bright as the full moon, it kind of washes out the fainter light from faraway stars.
Makes sense.
Yeah.
It's like trying to have a quiet conversation at a rock concert.
Yeah, exactly. Just too much going on.
So picture this. We've got the moon hanging out in Taurus, right beneath the horns of Aries the ram. And then a few hours later, Orion the hunter starts rising in the east.
Oh, it's like a celestial party getting started up there.
It really is.
And it's constantly changing, too. I mean, the moon's position shifts throughout the night because, the Earth's rotating.
That's right.
So we get these amazing relationships between the moon and the different constellations, like a slow dance across the sky. While we're talking about this celestial dance party,
Yeah.
we can't forget about some other VIP guests.
Who else is coming?
Well, we've got a whole planetary lineup joining the supermoon tonight.
Yeah, here.
I'm serious. Mercury, Venus, Saturn, Jupiter, they're all making an appearance.
Total planet parade. This night is unreal. Okay, so where should we look for these cosmic celebrities?
All right, let's start with Mercury.
Okay.
You'll find it low in the southwest, setting pretty quickly after the sun.
Oh, so you won't have much time to catch it.
Not really. And this is important. Never look directly at the sun, even during sunset. You need proper eye protection.
Yeah, those solar rays are no joke.
They can do some serious damage to your eyes, so be careful.
Good point. Safety first when we're stargazing. So Mercury's going to be a tough one to see. What about Venus?
Venus is much easier. That'll be the brightest object in the southwest, shining a bit higher than Mercury. You'll have maybe 90 minutes after sunset to catch it.
Cool.
It's kind of funny. Venus is often called Earth's twin, because they're similar in size and what they're made of.
I've heard that.
But Venus is not very Earth-like at all. It's got this super thick atmosphere. It's toxic, and the surface is crazy hot.
Yikes. Maybe not so twin-like after all.
Nope, not really. Okay, moving on from the twin to a planet with some serious bling, Saturn.
Where can we find it?
Saturn will be high in the south, glowing pale yellow. It'll be up there for a while, sitting after midnight.
Nice. Now, of course, we can't talk about Saturn without mentioning those famous rings.
Oh, absolutely. They're iconic.
I mean, can you believe those rings are made of countless particles of ice and rock, all orbiting the planet?
It's mind-boggling, right? Some are tiny like grains and others are huge like boulders.
It's incredible. Okay, while we're on a roll, where's Jupiter hiding?
Look for Jupiter rising in the east about 2 hours after the moon.
Got it.
It'll be visible all night, setting after sunrise. That gas giant is a real night owl.
Jupiter, the king of planets. You know, it's so big that it weighs more than all the other planets in our solar system put together.
It's true, it's massive. And it's got some pretty wild storms raging on it, too, like the Great Red Spot,
Oh yeah, that's been going on for centuries, right?
at least. And some scientists think those storms might actually be helping to regulate Jupiter's temperature.
So it's like a giant planetary air conditioner.
Pretty much, yeah.
Okay, so we've got Mercury, Venus, Saturn, Jupiter. Wait a minute.
What is it?
Is that Mars I see rising in the east just before midnight?
It is.
This night is unbelievable. Seriously, every planet is showing up.
I know, right? It's like they all decided to put on a show for us.
And you know what it makes me think of?
What's that?
Seeing all these planets together with this supermoon,
Oh,
it really highlights how connected everything is in our solar system.
absolutely. They're all bound by gravity, constantly pulling on each other.
A never-ending cosmic dance.
Exactly.
So we've got this incredible full Beaver Moon, a supermoon no less.
Don't forget those shimmering Pleiades.
Right, and then to top it all off, this amazing parade of planets.
Mercury, Venus, Saturn,
Jupiter.
even Mars making a late entrance.
This whole night is just mind-blowing.
You know, it's pretty amazing to think about. For thousands of years, people have looked up at the same sky and felt that same sense of awe.
It really makes you feel connected to, like, all of history.
It does. The moon, the stars, the planets, they've inspired so many stories, scientific discoveries, just quiet moments of reflection.
We're part of something so much bigger than ourselves.
Exactly. It's humbling, isn't it?
It really is.
Think about it. When you go out tonight and you look up at this incredible sky, you're connecting with a legacy of people watching the stars going all the way back, to the very beginning of humanity.
Wow, that's a powerful thought.
And you're also getting a glimpse of, this vast universe.
Filled with mysteries.
Exactly. So many things we still don't know.
Well, I don't know about you, but I am ready to go find a good spot to watch this show.
Me too. This is one you won't want to miss.
It really is a chance to connect with the universe, to experience that same wonder that people have felt for generations.
Absolutely.
So get out there and enjoy the show, everyone. All right, ready to dive deep into magnetic fields. They're everywhere. I mean, literally everywhere. Earth, planets, stars, the Milky Way even, all tangled up in these massive magnetic fields that stretch millions of light years. Mind-blowing, right?
Yeah, pretty amazing.
But what really gets me is how they got started. Where did these ginormous magnetic fields come from? That's the mystery.
Yeah, it's a fascinating puzzle. We've come a long way in figuring out how magnetic fields get amplified, how they grow stronger over time.
So we know how the fire spreads, but not what lit the match.
Exactly. Like we know how a wildfire spreads once it's caught, but not quite what sparked it in the first place.
Finding the source of those initial seed fields, huh?
Yeah, that's been a real challenge.
Well, that's what makes this new research so exciting. It's an astrophysical journal,
Uh-huh.
and it takes us way back to the very beginning, the cosmic dawn, just a few 100 million years after the Big Bang. And it's got this mind-boggling idea about a dust battery that could have sparked those very first magnetic fields in the universe.
Pretty wild, right?
It is. So tell me more. How does this dust battery work?
Okay, so picture this. The very first stars, giant short-lived stars, they explode as supernovas.
Okay.
And they scatter heavy elements everywhere, forming dust clouds across the young universe.
Got it, a universe full of dust.
Right, but this dust, it's not just sitting there. It's being bombarded with radiation constantly, and there are collisions causing the dust grains to get electrically charged.
Oh, I see. Okay, so now we've got electrically charged dust. But how does that create a magnetic field? That seems like kind of a leap, doesn't it?
Well, that's where the battery part comes in. A second generation of stars ignite, and their light, it's super intense, and it starts pushing against these charged dust particles.
The cosmic wind.
Yeah, exactly. Imagine a cosmic wind pushing on countless tiny sails. This movement of all that charged dust, even though it's super subtle, it creates this weak electrical current. It's kind of like a copper wire stretching across 1,000 light years.
Okay, hold on a sec. So we've got current flowing, but I'm still not getting how that makes a magnetic field.
think about the dust. It's not spread out perfectly evenly, right? So you've got some areas that have more current flowing through them than others.
Right.
And, from the laws of electromagnetism, variations in electrical current, they naturally create magnetic fields.
Whoa, so you're saying those tiny charged dust particles just being pushed around by starlight could have created the very first magnetic fields in the whole universe?
Yeah.
That's kind of a big deal.
It is. And the researchers estimate that those first magnetic fields would have been incredibly weak. We're talking maybe a billionth the strength of Earth's magnetic field.
Wow.
But the thing is, it's not about the initial strength. It's about having that initial spark, that seed.
Right, the seed.
Yeah, because from there, other processes can amplify those fields over billions of years. And that's what shapes the universe we see today.
Okay, so we've got this tiny dust battery that creates this faint magnetic field. But then what? What happens next? How does that tiny field turn into something strong enough to influence entire galaxies?
Okay, so think of the universe as a super turbulent place.
All right.
Gas clouds colliding, stars exploding, galaxies rotating.
Mhm.
All that motion is acting on those early magnetic fields, stretching them, twisting them, and that actually makes them stronger.
So the more the universe churns, the stronger those magnetic fields get.
Exactly. Then you've got this thing called the dynamo effect. Imagine a generator, but on a galactic scale, powered by the rotation of stars and entire galaxies.
Wow.
This dynamo effect, it amps up the magnetic field even more. And then you have this feedback loop where the movement makes the field stronger, and the field, in turn, influences the movement.
So it keeps building on itself.
Exactly.
Hold on, let me make sure I'm following. We start with dust, starlight pushes it around, creates a weak magnetic field, and then the universe just kind of churns it up and makes it stronger and stronger. Is that right?
You got it.
Okay, but this all seems pretty, well, speculative, doesn't it?
Yeah.
How do we know for sure this dust battery theory is even right?
You're right to be skeptical. It is just a hypothesis right now, but it's a really fascinating one. But the real test is going to come from computer simulations.
So you mean like virtually rewind the universe?
Yeah, exactly. And then plug in this new theory and see if it matches up with what we actually observe in the universe today.
Wow, so they build a virtual universe and hit play.
Pretty much, yeah. And if the simulations can recreate the magnetic fields we see today, well, that would be pretty strong evidence in favor of this theory.
So it's like a giant cosmic experiment.
Exactly. And who knows, there might be other mechanisms at work too. But this research, it opens up a whole new way of thinking about the origin of these fundamental forces that shape the universe.
It makes you wonder, what does it all mean for us? I mean, these events happened billions of years ago. Why should we even care about these ancient magnetic fields? They seem so far removed from our lives here on Earth.
Well, that's where it gets really interesting. See, magnetic fields, they're more than just these invisible forces. They influence how galaxies evolve, how stars and planets form, and even the conditions that make life possible.
Wait a minute. Are you suggesting that these early magnetic fields created by the dust battery could have actually played a role in our own existence? That's kind of a big deal.
It's a pretty exciting possibility. Just think about it. Magnetic fields can shield planets from harmful radiation.
Right.
They can influence the structure of those disks of gas and dust where planets form. And they even play a role in those stellar winds that carry the building blocks of life throughout galaxies.
So it's like this chain reaction across billions of years, all starting from those tiny dust particles. It's hard to wrap my head around how something as subtle as a magnetic field could have such a big impact on something as massive as a galaxy.
It's all about those long-term effects. Magnetic fields can exert pressure on gas. That means they can influence how it moves and how it's distributed within a galaxy. Imagine them like invisible hands shaping the flow of matter over these huge distances and incredible timescales.
So like cosmic architects.
That's a great way to put it. And it's not just the overall structure either. They can channel gas flows within a galaxy, influencing where stars form and even how those majestic spiral arms form, like the ones we see in our own Milky Way.
It's incredible. These invisible forces are weaving this intricate tapestry of the cosmos, shaping everything from the grand design of galaxies to the very conditions for life itself. But how do those ancient magnetic fields, the ones forged way back in the cosmic dawn, compare to the ones we see in galaxies today? Did they just fade away, or did they evolve into the powerful ones we observe now?
That's where things get really interesting. Remember, those initial seed fields were super weak.
Yeah.
To get to the strengths we see today, they needed a boost. And that's where those amplifying processes we talked about earlier come into play. Over billions of years, all that turbulence, the dynamo effect, and other things, they gradually amplify those fields, shaping the magnetic landscape of the universe we see today.
So like those tiny seeds planted in the cosmic dawn grew into mighty magnetic forests, shaping the universe as we know it.
Exactly. And just like trees, magnetic fields, they come in all shapes and sizes. Some galaxies have these incredibly strong, well-organized fields, while others have weaker, more chaotic ones. It all depends on the galaxy's unique history and the interplay of those amplifying mechanisms.
So it's like every galaxy has its own magnetic personality, a testament to its long and tumultuous past. What about our own Milky Way? What's the story of its magnetic field? Is it a gentle breeze or a cosmic hurricane?
The Milky Way's magnetic field, it's a fascinating beast in its own right. It's much weaker than Earth's magnetic field, but it stretches for tens of thousands of light years, encompassing the entire galaxy. Imagine this delicate but expansive web woven through every corner of our galactic home.
It's almost impossible to imagine. So
Right.
where did it come from? Did it spring from those early seed fields too? Maybe even the dust battery?
It's very likely that the Milky Way's magnetic field also originated from those faint whispers in the early universe. But over billions of years, it's been sculpted and amplified by the galaxy's rotation, the turbulent dance of its gas and dust, and even the explosive deaths of its stars. Imagine this grand cosmic symphony with all these different forces playing their part in shaping this intricate magnetic masterpiece.
It's incredible to think we're living within this vast, invisible magnetic web. It's a real testament to the universe's long and turbulent history. But how does the Milky Way's magnetic field compare to the ones in other galaxies? Is it typical, or is it kind of an outlier?
That's a great question, and it's one that keeps astrophysicists up at night. We're constantly observing and mapping the magnetic fields of other galaxies, trying to understand the diversity of their strength, structures, and origins. And what we're finding is that there's no one-size-fits-all answer.
So every galaxy's magnetic field is as unique as a snowflake.
Exactly. Some galaxies have magnetic fields aligned with their spiral arms, while others show a more chaotic and turbulent arrangement. Some fields are confined to the galaxy's disk, while others extend far into the halo, that vast region surrounding the visible galaxy. It's a breathtaking variety of magnetic personalities.
It's mind-boggling to think about all that diversity out there.
Yeah.
But how do we even detect these magnetic fields in the first place?
They're invisible, right? What tools do we use to map out these cosmic mysteries?
That's where the ingenuity of astronomers shines through. We can't see magnetic fields directly, but we can detect them through their subtle effects on light. They're whispers in the cosmic symphony, you could say. It's kind of like studying the ripples in a pond to figure out if there are fish swimming beneath the surface.
So we're looking for those telltale signs, the clues that betray the presence of these hidden magnetic forces. But what are those clues? How do we read the language of light to decode those magnetic messages? One of the key techniques we use is called Faraday rotation. Imagine light as a wave vibrating in a particular direction. When it passes through a magnetized region, its direction of vibration gets twisted, kind of like a corkscrew turning through space. By carefully measuring the amount of this twisting, we can work out the strength and direction of the magnetic field along the light's path.
So by carefully analyzing the light from distant galaxies, we can actually map out their magnetic fields even though we can't see them directly. It's like using light as a cosmic compass, guiding us through this invisible magnetic landscape.
Exactly. It shows the power of light. Not just to illuminate the universe, but to carry secrets, whispers of magnetism across billions of light years. But the story of cosmic magnetism doesn't end there. There's so much more to uncover, more mysteries to unravel. Shall we continue our exploration?
Absolutely. Let's dive deeper into this cutting-edge research.
So those simulations you mentioned are absolutely key to figuring all this out, to understanding the role of magnetic fields in the early universe. I'm curious, though, how do scientists actually go about recreating the conditions of the early universe? Like in a computer, it's not like we can just hop in a time machine and take some measurements.
Right. It's mind-boggling to even think about it.
Okay.
Creating a virtual universe and then hitting play to see how those early magnetic fields evolved. So how do they build this digital universe? Where do they even begin?
It's incredibly complex, that's for sure. Imagine trying to model the Earth's entire weather system,
Yeah.
but on a cosmic scale.
Whoa.
So researchers start by setting the stage, so to speak. They define the initial conditions of the early universe.
Okay.
based on what we know from observations of the cosmic microwave background radiation.
Which is?
That's the faint afterglow of the Big Bang. They input things like the density and temperature of the early universe and how matter was distributed, and of course, those initial seed magnetic fields.
Okay, so they've built the backdrop, set the stage. But how do they actually make the universe, evolve in the simulation? How do you simulate billions of years of cosmic history in a computer?
That's where supercomputers come in. They are incredibly powerful machines,
I bet.
capable of processing these huge amounts of data and running super complex calculations. Researchers use them to solve a set of equations that describe how matter and energy behave over time.
Okay.
And these equations, they capture those fundamental forces at play. You've got gravity pulling things together, the expansion of the universe pushing things apart, the formation of stars and galaxies, and of course, the evolution of those magnetic fields.
So it's like they've created a cosmic recipe book,
Yeah.
and those equations are the instructions for how the universe kind of bakes over time.
I like that, a cosmic recipe book.
You combine the ingredients, the initial conditions, and let the supercomputer do the mixing and cooking.
Exactly. It's like having a virtual time machine powered by equations and supercomputers.
It's incredible. But like with any recipe, you need to make sure it's producing the results you want.
Mhm.
How do scientists know if their simulations are accurate? Can we really trust them to give us a reliable picture of the early universe?
That's the million-dollar question. It's a universe that existed billions of years ago,
Yeah.
right? So that's where the real detective work comes in. Scientists are constantly comparing the results of their simulations to actual observations of the universe.
So they look for things that match up.
Exactly. Things like the distribution of galaxies, the characteristics of stars, and the properties of magnetic fields in the real universe. And then they compare them to what their simulations predict.
Okay.
And if the two line up, well, it gives us confidence that we're on the right track and that our understanding of the physics is solid. But if they don't match up, well, then it's back to the drawing board. Time to refine those models, tweak the recipe, so to speak.
So it's this ongoing process of refinement, of constantly checking and tweaking against reality.
Right. Science is all about testing ideas against observations, making adjustments as needed, and gradually getting closer and closer to the truth. And these simulations are such powerful tools in that quest. But even with our best supercomputers, we have to remember there are limits to what we can model.
Yeah, I imagine. What are some of the challenges that scientists face when trying to simulate something as complex and vast as the early universe?
Well, one of the biggest hurdles is just pure computational power.
Yeah.
Even the most advanced supercomputers have their limits.
Right.
And we can only simulate a relatively small portion of the early universe at a time. It's kind of like trying to map an entire continent using only a handheld GPS device.
You're going to miss some details.
You're bound to miss some detail.
For sure. Are there other limitations too?
Definitely. The complexity of the physics involved, that's another big challenge. We're still learning about those fundamental forces and interactions that govern the universe. And trying to capture all those nuances and all that complexity in our models, well, it's a really tough job.
So it's like trying to put together this giant jigsaw puzzle with some of the pieces still missing.
That's a great way to put it. We can see the general picture, but some of the details are still a mystery.
Right.
But, it's those missing pieces, those unsolved mysteries that really drive scientific curiosity. It's what pushes us to develop more and more sophisticated tools and models. It's a constant evolution of our understanding.
Okay, so speaking of evolution, let's shift our focus from the early universe to the present day. We've talked about magnetic fields shaping the first stars and galaxies. But what about their influence on galaxies we see around us now? Are they still actively shaping the cosmos, or have they kind of faded into the background?
Magnetic fields are far from passive bystanders. They still play a huge role in the life of galaxies, even billions of years after they formed. Think of them like the invisible scaffolding that supports a galaxy. They influence its shape, its structure, and its evolution over these vast stretches of time.
So they're not just relics of the past, but active players in the ongoing cosmic drama. But how do they actually exert their influence? What kind of impact are they having on galaxies today?
One of the biggest things is regulating star formation. They act like cosmic traffic cops. They direct the flow of gas within a galaxy and influence whether or not those swirling clouds of gas and dust will collapse and form new stars.
So they're like the architects of stellar nurseries, deciding where and when those cosmic cradles will give birth to new stars.
That's a great analogy. In some regions of a galaxy, magnetic fields can actually help funnel gas into these dense clouds, creating the perfect conditions for star formation to really take off. But in other regions, they act as barriers. They resist the collapse of gas clouds and actually suppress star formation.
It's incredible that these invisible forces have so much power over the birth and death of stars. But how do they actually do it? What are the mechanisms at play?
Well, one of the key players is magnetic pressure. Magnetic fields can push back against the inward pull of gravity. They resist the collapse of gas clouds and prevent stars from forming. It's kind of like trying to squeeze a balloon, you know? The air inside pushes back, making it harder to compress.
So it's like a cosmic tug of war,
Yeah.
with gravity trying to pull matter together and magnetic fields pushing back, resisting that collapse.
Mhm.
And depending on which force wins, you either get a burst of star formation or a quiet period.
That's exactly right. And the outcome of this cosmic battle really depends on the strength and the configuration of the magnetic field. It's this delicate interplay between gravity and magnetism that creates this beautiful diversity of star-forming regions that we see across galaxies.
It's amazing to think about these invisible forces having such a profound impact. We've been focusing on star formation, but what about the galaxies themselves? How do magnetic fields influence their overall shape and structure?
That's another area where they play a huge role. Magnetic fields influence a galaxy's rotation, how its stars and gas are distributed, and even how it interacts with other galaxies. They're like cosmic sculptors, shaping the grand design of galaxies over billions of years.
So not only are they influencing the birth of stars, but they're shaping the very galaxies that house those stars. They're involved in the big picture and the small details.
Exactly. For example, magnetic fields can actually help create and sustain those majestic spiral arms that we see in galaxies like our own Milky Way.
Right.
They can also help to confine the gas and dust in a galaxy's disk, preventing it from being blown away by the fierce winds from massive stars or those incredibly powerful jets from supermassive black holes.
So they're kind of like the guardians of galactic integrity,
Yeah.
holding everything together and guiding their evolution over these vast cosmic timescales.
That's a great way to think about it. They even play a role in those dramatic events where galaxies collide and merge, influencing how those interactions play out and what the resulting galaxies will look like.
It's mind-blowing to think about this intricate dance of forces. Gravity's pulling, magnetic fields are pushing, stars are exploding, gas is swirling. It's all shaping this grand cosmic ballet. But I can't help but wonder, how do we actually know all this? How do we study these invisible fields in distant galaxies, especially when they're so faint and elusive?
That's where the ingenuity and persistence of astronomers really shines. We've developed a whole arsenal of clever techniques to study these elusive fields, even across these vast cosmic distances. And one of our most powerful tools is Faraday rotation, which we touched on earlier.
Right, that's where the light's polarization, its direction of vibration gets twisted as it passes through a magnetized region. It's like a cosmic compass needle aligning with those magnetic field lines.
Exactly. And by carefully measuring how much that polarization has been rotated, we can figure out the strength and direction of the magnetic field along that light's path through the cosmos. We also use other techniques like studying something called synchrotron radiation.
Synchrotron radiation.
Yeah, it's emitted by charged particles spiraling around magnetic field lines, and we can use that to map out their distribution in galaxies.
It's amazing. So we're using light itself, those photons traveling for billions of years, as messengers carrying information about magnetic fields across this vast expanse of space. It's almost poetic.
It is. It's a real testament to the power of human curiosity and ingenuity. And with ever-improving telescopes and techniques, we're getting better and better at detecting and studying those faint magnetic whispers from the distant universe.
And it's incredible what we've learned and how much more there is to discover. I want to circle back to something we talked about earlier, the connection between magnetic fields and life. You mentioned Earth's magnetic field acting as a shield, protecting us from harmful radiation from the sun, making life as we know it possible.
Exactly. Our planet's magnetic field is like this giant invisible force field. It deflects all those charged particles from the sun and those cosmic rays that could really mess with our DNA and disrupt that delicate balance of life. Without it, life on Earth would be constantly bombarded by all this harmful radiation, and it would make it much harder for complex life to evolve and thrive.
It's like our planet has its own personal bodyguard, a magnetic shield protecting us from the dangers lurking out there in space. But could these magnetic fields be more than just protectors? Could they have actually played a role in the origin of life itself?
Now, that's a fascinating question, and it's a question that's driving a lot of research right now. Scientists are exploring whether magnetic fields might have been essential for life to even emerge on Earth. Think about the early Earth being bombarded by radiation. Those magnetic fields could have provided safe havens,
Oh, I see.
shielding delicate molecules and allowing them to assemble into the building blocks of life.
So instead of just protecting existing life, magnetic fields might have actually helped those first sparks of life to ignite. That's a pretty revolutionary idea.
It is, and it leads to even bigger questions, like how common are magnetic fields around other planets? Do most planets have protective shields like Earth, or are we kind of an anomaly?
Right.
And if magnetic fields are really a prerequisite for life, well, does that mean that life is more likely to emerge in certain types of galaxies, in environments where these fields are stronger or more common?
Those are some really big questions. It
Mm,
seems like we've only just started to scratch the surface of this cosmic mystery.
absolutely. The exploration of magnetic fields and their connection to life, well, that's one of the most exciting frontiers in astrobiology. There's still so much more to discover, and with all those new telescopes and missions coming online, I'm confident we'll be uncovering even more secrets about these invisible forces in the years to come.
It's an incredible journey, and we're just getting started. We've explored how magnetic fields shape galaxies, how they govern the birth and death of stars, and how they might even hold the key to understanding the origin of life itself. But our journey through the magnetic universe, it isn't over yet. There's one final realm we need to explore, the domain of the most extreme objects in the cosmos, black holes.
Black holes, those cosmic enigmas where gravity reigns supreme. Get ready, because when it comes to magnetic fields and black holes, things get really wild.
I'm ready. Let's dive into the heart of these cosmic behemoths and see what secrets their magnetic fields hold.
So black holes, regions of spacetime where gravity is so intense that nothing, not even light, can escape. They're often portrayed as these cosmic vacuum cleaners just relentlessly sucking in everything around them.
Right?
But that's only part of the story. Black holes are also incredibly dynamic objects. They've got these powerful magnetic fields swirling around them, generated by the very matter they consume.
So it's not just a one-way street. It's not just about stuff falling in. Black holes are pushing stuff out, too.
Yeah, you got it. It's this cosmic balancing act.
Okay.
Black holes are voracious eaters, pulling in gas and dust from their surroundings. But this creates this swirling disk of matter around the black hole, kind of like water circling a drain.
Okay.
And as all that matter spins and spirals inward, it generates incredibly strong magnetic fields.
So we've got this swirling vortex of matter creating these intense magnetic fields around the black hole. But how do those fields actually affect the black hole itself? Are they just along for the ride, or do they actually play a role?
Oh, they're not just passive bystanders. Those magnetic fields, they can influence how the black hole feeds, how it grows, and even how it launches those spectacular jets of matter and energy.
Okay, those jets. They've always confused me. How can a black hole with gravity so strong nothing can escape shoot out those powerful beams of matter? Just seems impossible.
It is a mind-bending concept, but those magnetic fields are the key. Imagine them as these super powerful cosmic slingshots, accelerating particles to nearly the speed of light and flinging them out from the poles of the black hole in these narrow, focused beams.
So they're like cosmic particle accelerators shooting these jets of matter across huge distances.
Exactly.
It makes the particle accelerators we build here on Earth seem pretty tiny. But how far can these jets actually reach?
We're talking mind-boggling distances here. Hundreds of thousands of light years, sometimes even millions.
Wow.
Imagine a beam of light traveling for 1,000,000 years. That's the scale of these jets. And they can pierce through entire galaxies, leaving these glowing trails of energized particles behind, like cosmic contrails.
It's hard to even picture something that big, but that sounds like more than just a light show. Those jets must be having some sort of impact, right? What role do they play in the universe?
Oh, they're far from just a cosmic spectacle. These jets can have a huge impact on their surroundings. They can actually heat up the gas in nearby galaxies, preventing it from cooling and collapsing to form new stars. But in other regions, they can actually trigger star formation by compressing gas clouds. It's like a cosmic sculptor molding stellar nurseries.
So they're kind of like cosmic gardeners, pruning and planting stars across the universe. It's fascinating how something born from a black hole, a region of such intense gravity, can actually influence the creation of new stars and galaxies.
It really shows how interconnected everything in the universe is.
Yeah.
These seemingly isolated black holes with their intense magnetic fields and powerful jets can have ripple effects that influence the evolution of entire galaxies. They're key players in the grand cosmic drama.
Speaking of playing a role,
Yeah.
you mentioned earlier that black holes can grow.
Yeah.
How do magnetic fields factor into that process?
Well, black holes grow by consuming matter, right? Pulling in gas and dust from their surroundings. But it's not always a smooth and steady process. And those magnetic fields we've been talking about, they can actually regulate how efficiently a black hole feeds.
Oh, I see. So they're like the gatekeepers of the black hole's feast, controlling how much it can devour.
That's a perfect way to put it. In some cases, magnetic fields can channel matter smoothly into the black hole, fueling its growth. But in other cases, they can create turbulence and resistance, actually slowing down the process and even flinging some of that matter back out into space. It's like this cosmic dance, this push and pull between gravity and magnetism.
So it's this delicate balancing act. Sometimes the black hole wins and gobbles up the matter, and sometimes the magnetic fields win and put the black hole on a diet.
No. Exactly. And this delicate interplay has huge implications for how black holes grow and how they affect the galaxies around them. But let's zoom out for a moment. We've talked about magnetic fields on the scale of planets, stars, galaxies, even black holes. But what about the universe as a whole? Could magnetic fields exist on a truly cosmic scale?
Now that's a mind-boggling thought. A magnetic field stretching across the entire universe. But how could something like that even form? And how would we even know if it exists?
It's a question that's driving some of the most exciting research in astrophysics. There's growing evidence suggesting that magnetic fields might actually permeate the entire universe, forming this vast interconnected web of cosmic magnetism.
Wow, a cosmic magnetic web. So we're not just talking about little pockets of magnetism here and there, but a truly universal magnetic field. Where could something so vast have come from?
Well, it's thought that these cosmic magnetic fields might have originated in the very early universe, perhaps even during the Big Bang itself. Imagine the universe in its infancy, this hot, dense soup of particles. Tiny fluctuations in this primordial soup could have generated these weak magnetic fields.
So we're talking about magnetic fields woven into the fabric of space-time itself, stretching back to the very beginning of time. It's hard to imagine how we could even detect something so ancient and elusive.
It is a huge challenge, but astronomers are coming up with some really ingenious techniques to probe this cosmic magnetic web.
Okay.
One way is to study the polarization of light from really distant galaxies and quasars, those
Quasars.
incredibly bright beacons powered by supermassive black holes.
Right, so we're back to Faraday rotation. That twisting of light's polarization as it travels through these magnetized regions. It's like using light itself as a probe to map out these invisible magnetic fields.
Exactly. And by analyzing the polarization of light from many different sources across the sky, astronomers are piecing together a map of this cosmic magnetic web, revealing its structure and strength on the grandest of scales. It's like creating a magnetic map of the universe.
It's incredible to think that we can use light, traveling for billions of years, to map out a magnetic field that's been around since the universe's birth. It's amazing. But what have we learned so far? What does this cosmic magnetic web look like?
Well, we're finding that it's definitely not uniform. It has regions of stronger and weaker magnetism, places where the field lines are tangled and twisted, and others where they flow more smoothly. It's a really complex and dynamic structure, constantly evolving and influencing the cosmic landscape around it.
So it's not just this static web hanging out there, but this dynamic force shaping the universe on a grand scale.
Exactly. And understanding this cosmic magnetic web, well, it's key to understanding the evolution of the universe itself. It might have even played a role in the formation of those first stars and galaxies. And it influences the distribution of cosmic rays, those high-energy particles zipping through space. And it might even contribute to dark energy, that mysterious force that's accelerating the expansion of the universe.
It's incredible to think that something we can't even see could have such a huge impact on the universe. From the tiniest particles to the largest structures, it really shows you how much we still have to learn about the universe and the forces at play.
Absolutely. And the study of magnetic fields is a rapidly evolving field. With all these new instruments and techniques being developed, we're really on the cusp of unlocking even more secrets about this invisible force that permeates the universe. It's an exciting time to be an astrophysicist.
I bet it is. It's been an amazing journey exploring the magnetic universe with you. We started with those tiny electrically charged dust particles in the early universe, then moved on to the powerful fields shaping galaxies, and finally to the dance of black holes and their jets. But before we wrap up, I want to bring it back to our listener. Why should all of this matter to us here on Earth? Why should we care about these invisible magnetic fields?
I think there are many reasons to be fascinated by magnetic fields. First, it's a real testament to how interconnected everything in the universe is. Magnetic fields, from the smallest scales to the largest, weave this cosmic web that connects us all, influencing the birth and death of stars, the evolution of galaxies, and even the conditions for life itself.
It really is a beautiful reminder that we're not isolated beings on this lonely planet, but part of something much bigger, this grand cosmic tapestry.
Exactly. And it's a story of discovery. It's about pushing the boundaries of what we know. We're constantly learning new things about magnetic fields, revealing their hidden influence, and unlocking secrets about the universe that have been hidden for billions of years. It reminds us that there's always more to learn, more mysteries to unravel, and that the pursuit of knowledge is an endless and incredibly rewarding adventure.
It's a journey that fills us with wonder and reminds us of the power of human curiosity.
And lastly, it's a story about our own origins. As we've discussed, magnetic fields might have played a key role in the emergence of life on Earth, and they might be essential for life to exist elsewhere in the universe. By studying these invisible forces, we're not just exploring the cosmos, but also exploring our own place within it, our connection to the universe and its intricate workings.
It really is a humbling thought that something as invisible and distant as magnetic fields could have played such a major role in our own existence.
It is. It reminds us that we are part of something so much greater than ourselves, a universe full of wonder and mystery. And our journey of exploration and discovery, well, it has really only just begun.
And on that note, I think we've reached the end of our deep dive into the magnetic universe. It's been an incredible exploration, and I hope our listeners have enjoyed the journey as much as we have.
It's been a pleasure sharing this fascinating topic with you and the listeners.
And remember, the universe is full of wonders, both seen and unseen. Keep looking up, keep asking those questions, and never stop exploring. Who knows what other mysteries are waiting to be discovered in the vast expanse of the cosmos?